Okay, we are still in section 2.2. We're going to pick up where the last video left off. We had just started discussing how to find the area underneath a normal distribution. These were standard normal distributions, meaning the z-scores here were down along the x-axis. If you recall, the mean of a set of z-scores is always 0, and the standard deviation is always 1. Okay. And we were becoming familiar with how to use this table, which always works by calculating the area under the curve to the left of a specific z-score that you're looking up here. Okay, so let's pick up where we left off here. We want to use this table A. In example C, we are looking for the probability that a z-score would fall below 0.86. And so again, on these problems, we always want to draft a bell-shaped normal curve. Since we're doing z-scores, you would label down the middle that the mean is 0. Okay, again, one standard deviation should fall right at that change in curvature, that point of inflection. This would be a 1 on this side. This would be a -1 on this side. And so we're looking roughly 0.86. 0.86 would maybe fall right about here. Okay, and we want to find the area to the left of 0.86, okay, area to the left of 0.86, and so you would go to, now I only included up above here a small section of one of the tables. So you were given a formula sheet. There's also access to, on the web page, a link right on the home page there of how to get to the formula sheet. Okay, one page is all the negative z-scores. Okay, that's this first page here, and then the next page is all the positive z-scores. I believe our z-score on this was 0.86. So you would look along the left side, go down to that first column where it says 0.8, and then move across the very top row, look for the hundredths place 0.06. You're going to look where those two things are colliding each other. Looks like that's right there at 0.8051. So we're going to come on back to this, and we're going to fill in the area to the left of that. I'm going to just label it like this, would be roughly 80.5% of the data. Okay, you can see on the next example, I went ahead and completed that one there for you. Again, this is a homework assignment that you should have been able to probably complete most of those from the previous video. Okay, let's jump on down to example E here, because this one is a little bit different. At this point, all of the problems have been asking us to find that area that has been to the left of the z-score, and they've used a less than symbol here, but now we have a greater than symbol. Okay, so let's go ahead and label. We got 0 here. Here would be one standard deviation to the left of the mean, but we're just looking at just a hair to the left of the mean, -0.17, but the area is everything to the right of that. Okay, now here's what we're looking for. I'm going to go ahead and label this here. Everything to the right of a z-score of -0.17. If you recall, we said the area underneath the entire curve is 1 for 100% of the data. Okay. When you use the table, though, the table is going to give you the area to the left if you look up -0.17. Okay. If we know the whole area is 1 and we subtract off all the area that is less than -0.17, that would leave us with all of the area to the right of -0.17. Okay, so we're going to look up -0.17 on our formula sheet here. So I want to flip to the side that's got the negative z-scores. -0.1 on the left side. Okay, that brings me right down to here. And then 0.07, I want to look up here at 0.07. Okay, I want to look where those two collide. It looks like it's an area of 0.4325. Okay, now again, that's not the answer. 0.4325 is the area to the left of the z-score -0.17. You would then subtract that off of 1, and that would roughly give you an answer of 56.8% would be the area there. Okay, so you see how we did that. We have to kind of subtract the area from the left of the z-score, subtract that off of 1 to get any areas to the right of the z-score. Okay, let's try another one here. Okay, we've got our mean of 0. Here's 1 standard deviation. Here would be 2 standard deviations, and we're going to mark off going a little bit more than that. Okay, this is almost including almost the whole curve here. I want all that area to the left. That means I don't want to count that little itty-bitty part there in the tail. Okay, so I'm going to do 1 minus the probability that a z-score is to the left of that. Okay, at this point, hopefully you're comfortable with using the table. You should go to your table. You would want to look along the left side for a z-score of negative 2.3. Go across the top, look at the column 0.03. Those two should collide at a z-score of 0.0099. We subtract that off of 1, and that gives us the probability that a z-score is to the right of negative 2.33 would actually be about 99%. It's almost all the curve anyhow. Okay, so we talked about how to find the area to the left of a z-score. That comes straight off the table. Okay, these few examples here, we talked about how to find the area to the right, how we subtract the area to the left from 1. But let's look at this example where they're asking us to find the area in between two z-scores. Okay, now I'm going to illustrate this for you by drawing 3 curves, but in all actuality, you would draw 1, which we'll start doing after this example here, and you just shade the area in between. Okay, so here's what we're after. Okay, I'm going to go ahead and mark 0 down the middle. Okay, and we want any of the area that's to the left of 1.90. Okay, so we're going to call 1.90 maybe roughly right about here. That's a z-score of 1.90, and I'm going to shade all of that in. Okay, so I'm going to write directly under that, that's the probability that a z-score is less than 1.90. Okay. However, if you look at this graph, and we'll look that up here. I think if you look it up in the table, 1.90, that area is 0.9713. Okay. But I don't want the area all to the left of 1.90. I want to stop when I get to 0.32. Okay. So over here on this next graph, I'm going to label where maybe 0.32 would fall. We're going to call it maybe roughly there. And I'm going to shade in all the area to the left of 0.32. This will be the probability that z is less than 0.32. If you look that up in the table, should come out to 0.6255. Okay, now this is the area I don't want to count. I only want the area to the left of 1.90 and then stopping when it gets right here to this barrier. So I'm wanting to subtract the 0.6255 from the 0.9713, and that actually gives me, and this last picture would really be the picture that you would just draw to begin with here, okay, of just the two z-scores with shading in between. That gives us 0.3458 or 34.6%. Okay. All right, so let's try another one like that without drawing all 3 of those, but you kind of get the idea that that's what's happening when you're doing that subtraction here. Okay, so I'm going to put 0 down the middle, 0.25 here, 0.86 there. Always shade the area that it's referring to. Okay, I want to take the z-score that's the area that's to the left of 0.86, and I want to subtract from that the area to the left of 0.25. If I look those areas up, these are the areas that I get, and that gives me an answer of 0.2064 or 20.6%. Okay. You can see on the next page a couple more examples. Here's another one in between two z-scores. Here's one that's to the right. And I went ahead and worked that out, but just so that you have a few more examples to look at. Okay. Now, we're going to apply this idea to a word problem here, example 3. It says, in the 2008 Wimbledon tennis tournament, Rafael Nadal averaged a 110 mile per hour on his first serves. Assume that the distribution of his first serve speeds is normal. Now that's very important, okay? We're assuming that this is a normal distribution. By the way, when you use this table, it is under the assumption that you see how this table A is called standard normal probabilities. You could not use that table if your data is skewed or anything like that. It has to be this bell-shaped normal curve. Okay, so this is the problem's way of telling us it's okay for you to use that table. Okay, it mentions that the average of his first serve speeds was 115 miles per hour, the standard deviation 6.2 miles per hour. The question about what proportion, which is just another way of asking the area under the curve, about what proportion of his first serves would you expect to be less than 120 miles per hour and then greater than 120 miles per hour. Okay, so the first question is draw and label a normal curve with the mean and the standard deviation on it. Okay, so we're going to draw a bell-shaped curve directly down the center. We're going to put his mean of 115. I'm going to look at the standard deviation of 6.2, and I'm going to go ahead and mark off 1, 2, 3 standard deviations on each side of the mean. Okay, and this is where you would simply add 6.2 and then add another 6.2 and then you would subtract 6.2, etc. We would get these values here. Okay, so I'm going to go ahead and fill these in. Okay, there, whoops, sorry. The screen kind of jumped. I think this would be 0.6 there. Okay, this would be 108.8, 102.6, and finally 96.4. Okay. So there we have this labeled, okay? That's number 1. Okay, number 2, you can see here is our z-score formula, something we definitely want to make sure that we memorize and commit to memory. Keep in mind the x is your variable, an individual value that you're trying to convert to a z-score, then mean and standard deviation. Okay, it wants us to calculate the z-score. Okay, we're going to do this for 120 miles per hour. Okay, I'm going to throw that up here on our graph where 120 would maybe land. It looks like maybe it would fall roughly right about there. So I'm going to squeeze that in up here at the top. That's where 120 is. Okay, now it was asking for what's the probability, first of all, that his first serves, we're expecting them to be less than 120 miles per hour. Okay, so initially we're talking about like the shaded area to the left. So I want to change this 120 into a z-score. That's what number 2 is telling us to do here. So we're going to plug 120 in for the x, subtract the mean of 115, divide by the standard deviation of 6.2. That means the z-score for 120 mile per hour first serve is 0.81. Okay, part 3 says determine the p-values. These are the proportion or the probability of it being less than 120 and greater than 20 by looking up the z-score in the standard normal curve. Okay, so we want to find what's the probability that his serve is less than 120, and then also what's the probability that it's greater than 120. Okay, now remember, 120 is not the z-score. Okay, the z-score is 0.81. Okay. So when we say what's the probability that his first serve would be less than 120 miles per hour, we're really wanting to find what's the probability that the z-score would be less than 0.81. And here we're saying z-score would be greater than 0.81. Okay, we would go to the table. Of course, we know if it's a less than problem, we can pull the answer right off the table and we're done, because that's how the table works, area to the left. So you would look up 0.81 on the table. You would see that would be 0.7910. If you were doing the greater than, now you're talking about this area over here on the right, so you would do 1 minus the area to the left. That would give you 0.209. Okay, now we're going to conclude this in context, which is what AP Statistics is all about, assigning some meaning here to what these numbers mean. We could say we expect that 79.1%, let's give some context, what are we talking about, of Nadel's first serves will be less than 120 miles per hour, and 20.9% will be greater than 120 miles per hour. Okay? Okay, hopefully this is making sense to you. We are going to do one more example, quite similar to the one that we just did there, and that will bring this video to a close and allow you to hopefully attempt a few of these problems here that kind of fall into this type of problem here. Okay, now we're talking about Tiger Woods. It says he hits his driver, and the distance that the ball traveled can be described by, and then look at this notation. This is statistics way of kind of telling us the shape and the center and the spread. Remember, this n is telling us this is a normal distribution. Okay, the reason that's important is that allows us to use table A to find these areas. Okay, we know it's not skewed. Okay, the first number is the average distance, the mean, and the second number is the typical spread, which is 8. Okay, this is in yards. It wants to know what % of Tiger's drives travel between, so this is a between problem, 305 and 325 yards. Okay, so we're going to start by drawing the distribution just like we did on the other problem here. Okay, we're going to fill the mean down the middle here. That's the 304. Okay, I'm going to go ahead and mark off 1, 2, and 3 standard deviations on the left. I'm going to go ahead and do the same thing on the right. Okay, when we fill these in, our standard deviation is 8, so we add 8 3 times on this side, subtract 8 3 times on that side. Okay, that's where I'm getting these numbers that you're seeing me write down here. Okay, this is 3 standard deviations on each side. By the way, when you go out 3 standard deviations on each side of the mean, remember the empirical rule says you've almost counted 100% of the data. It's like 99.7% of the data. Okay, step 2. Z-scores. Okay, before we do Z-scores, let me mark off, we're looking for between 305, so that's like maybe right there. I'm going to label that 305. That's a 0. Let me make that a little bit clearer here. 305. Okay, to 325, we're going to say that's right about here. Okay, and I'm going to go ahead and I'm going to shade in the area in between those two values. Now, keep in mind, those numbers, 305 and 325, those are not z-scores. That's why step 2 says we're going to change these to z-scores. Keep in mind, this is our z-score formula. Okay, so to change the 305 into a z-score, that's going to look something like this. And then to change the 325 into a z-score, that would be this. All right. Okay, so I'm going to write those down. I like to always add those onto the picture here. This z-score is 0.125. This z-score is 2.625. Now we're looking for the area in between those. Okay, so remember how this works here, and I'm just going to squeeze this right here. We want the probability that z is less than 2.625, but then we subtract from that the probability that z is less than 0.125, and that leaves us with the area in between. Okay, so we would go to our table, we would look up, now the table only goes out to the 10th place, so you're going to have to look up 2.63. That's what you're going to have to look up here, 2.63. Okay, so we look that up, we get 0.9956. We look up the area to the left, you'll have to look up 0.13, you'll have to round that there. Okay, that is 0.5478. Okay, that gives us an answer of 0.4478. Okay, so we're going to conclude this in context and just say about, you could say 45%, or if you wanted to say about 44.8% of Tiger's drives travel between 305 yards and 325 yards. It's better that you, when you're explaining the context, that you use yards than that you say 44.8% of Tiger's drives travel between a z-score of, and then use these z-scores, okay? It's better context to talk about it in yards, okay? And the last part of this, part B, says if Tiger hits his driver 256 times, okay? So he's going to take 256 tries at this. How many of those 256 would we expect the ball to travel between 305 and 325? Okay, remember how I told you with the free response questions on the AP test, a lot of times the parts tend to build? Let's look at what our answer was for part A and think about what that represents. It's saying 44.8% of the time, Tiger's drives travel between 305 and 325 yards. Okay, if he's going to attempt this 256 times, then we would multiply 0.448 times 256, okay, and I don't have that answer here, but you would multiply those two together, and we would say about, and you could round that up to, that is about how many times of the 256 that we would expect the ball to travel in between there. And you just have to multiply those together to kind of fill that in. Okay, that brings this video to a close.